screen.
Okay. So thanks a lot for Zhendong's introduction. I'm very happy to be here. And after hearing this morning's talks, I feel a little bit bad because there's no formula in my talk. There's no math in my talk. So what I hope for is maybe you will see some of the, I will talk about problems in software, so hopefully you will see some funny mistakes that are made by developers, and I just hope that you will have fun. Okay, so my talk is about why do big data and cloud systems slow down and stop. The first thing is a little bit of clarification, what exactly are big data and cloud systems? Different people have different answer. If you ask the database people, I think they will tell you it's everything related to these networked database systems. If you ask the system people, there are a lot of Hadoop, MapReduce, all these systems. So in our research, so today I will tell you a little bit of both. The first part of my talk will be talking about database-backed web application. And then at the end, I'll briefly talk about some of the research we did for these cloud service. So first of all, what do I mean by database-backed web application? So you may or may not realize there's actually most of our web applications, there's a database backend. What do I mean is that when you look the browser, you type a URL there, the request will be sent to an application server. And today's application, there is a non-trivial computation that will go on in the application server. And most of the time, the application server maintains, because your web applications these days are maintaining a lot of data. So a lot of times there will be a database request sent to the database server, and the query goes back, and then finally the result gets rendered in your browser. So for these applications, performance is critical, right? Because it's the end user that is looking at the browser. It's not a scientific computation or something. So there's always this, from long time ago, people believe that people expect your web result to come back in 2 seconds to remain interactive. And there's also all kinds of study telling you that if you get even 1 second of delay, right, there's a huge implication to the business. And things are getting harder and harder, right? In the past, when your web is just static, you just need to fetch the image, right, quickly. But these days, because there are a lot of data, so here's just some number that just tells you the data that are maintained by a website, it grows exponentially. So this performance has to be delivered, right, at the same time when the data need to be processed goes up. So it's a big challenge. Okay, then switch to the cloud service side, right? I'm sure you all know these days all kinds of things are done in the cloud. So this is just a screenshot about Microsoft Azure, what they offer. There are some database saying all kinds of analytic, IoT, storage, web, everything. And similar services are offered by all these different places. And then here, reliability, right, which is what I will talk about briefly. Reliability is really important. I'm not saying performance is not, right, but it's just I will tell you something about on the reliability side. These days, because a lot of computations move to cloud, so naturally, if anything wrong, the cloud service infrastructure, right? If they have a bug there that cause availability problem, get an outage, you get a huge loss. Okay, so that's what I will talk about. I will talk about some of the research that we did to understand what caused slowdowns in database-backed applications, and then we will talk about what we did to try to solve these problems. And we find during this process a lot of study, tool building. We find more than 1,000 inefficiency bugs in very popular open source web applications. A lot of this work, for the first part, a lot of work is done through the collaboration with Alvin, who actually is in the room, and I will mainly talk about that, and then at the end, I will use a few minutes to tell you, we also did a study in our collaboration with Microsoft to understand what stops, what caused outages in the production Microsoft Azure system. And we tried a lot of different things to try to solve those problems. And we're finally getting some exciting results. So in the SSP paper that we will present later this month, we were able to find, again, more than 1,000 bugs in Microsoft Azure code. Okay, so several pieces of work that I will talk about today, actually, they were all featured in the morning paper blog, and I found that they actually gave a much better summary than what I could give. So if you're interested, you can check those blogs. Okay, so going back to the first topic, what slowed down database-backed web application? So before I tell you what we found, let me give you just a little bit more background. And from that, you can see where problems can potentially happen. So going to a little bit more detail. So when a user type a URL to the browser, what would happen is the URL actually will indicate, will be interpreted, and so that the corresponding, like this index, right? So the corresponding method will be called. So this part is still just regular things. Now, in this particular thing, so I assume here that there's a blog website, and at some point there's this blog.retrieve. Now, this blog object happens to be a special object that is associated with database. So in this function, you will see that there's a call, blog.where. Okay, at this point, it still looks just a normal, right, object-oriented code. But this where, actually, it will be translated by the runtime inference framework to a SQL query. And this SQL query will be sent to, the database and be sent to a table. The name is blogs, okay? So it's the same name as a class name. And then the query will retrieve, the query will return some records from the database. And then this will be turned, you get something from the persistent database, right? They will be turned into objects. And then these objects that are retrieved from database then will be referred to by a web page. So then this web page then generates the content that the user would see. Okay, so that's the whole process. And you may already see, actually there's some quite subtle things here that are really not easy for developer to reason about. The first thing is this called Object-Relational Mapping Framework, ORM, that is very popular for this kind of web application. The idea is you have this magical, okay, ORM that automatically turns certain type of class into database table. So every field, every property you specify for the class, they become columns in the database table. And then correspondingly, there will be certain APIs. The developer may not even realize this, that at runtime will be turned into SQL query. Okay, so that's the first gap. So that's the first gap, kind of like the semantic gap or performance understanding gap here, right? Can developers really know, right, which API call will be turned into SQL query and how complicated are those SQL query? The second gap that I want to point out here is those developers who write these the web page code, right, mainly HTML code, right? In your HTML code, you will refer to some object, right? These are just like Ruby. So sorry, the language I was referring to, this application is written in Ruby on Rails. So this is just looks like just a regular Ruby object, right? But in this particular case, these Ruby objects, right, to get this object's content, you actually have to go through database. So the people who design the web page, right? Do they really realize what's the cost in generating this web page? So that's another, and you will see. So there's another understanding gap that can potentially lead to problems. Okay, so that's enough about the background about today's web application. So what next I will tell you is, first I will tell you we did a study about how severe is a problem. So we did a profiling, comprehensive profiling for 12 Ruby on Rails applications, which are the most popular applications from 6 common categories. And we find, through our profiling, we manually find performance problems in the latest version of these applications. And then we did we create a taxonomy, and we find, we call it performance anti-pattern, and we find 9 such patterns. And then we naturally, right, then after we find this pattern, we build static checker to automatically identify those patterns, and we identified more than 1,000 such problems. Okay, so the first thing, very quickly, so we go to, the students go to GitHub, and we look for, so these are the 6 most popular categories of web applications on GitHub, and for each, we look at the 2 most popular applications. And then we, the student synthesize database content based on, actually, this is a quite time-consuming manual process. So we go to those popular applications to get some statistics about, say, for example, if it's a shopping site, right? We look at how many products are listed for every product. Usually, what's the distribution, about the number of review, and so on. And then we synthesize our own database content to match those real-world statistics. And then we did a profiling, right? There are a lot of results, but the takeaway message is, for these, for 11 out of these 12 most popular applications, they contain, for most of them, right, they contain page that takes more than 2 seconds to load. And also to keep in mind, so these results are based on our synthesized database, that the main table, database table, contain 20,000 records, which is smaller than the popular deployment of all these applications. So in real world, the problem is more severe. And even worse, right? Half of these applications have pages that take more than 3 seconds to load, right? And then here, I want to remind you, remember 2 seconds is actually the magic cutoff about how likely that user will be happy with the performance. And then why is it slow, right? You may think, hey, maybe there's just too much things to do. Not really. So again, we manually checked. There were the worst pages that takes longer than 2 seconds to load. And we found that in most cases, we can, so these are all manual results. So we manually came up with performance patch. And in most cases, with less than 5 lines of code, we can improve the performance by many times, right? So these are all times. It's not, so we can do a speed up of the end-to-end loading time by several times. So there are different colors because these eventually they will map to different inefficiency patterns that I will talk about, but you can ignore them now. So the takeaway message is there is a lot of inefficiency problems in the latest version of this most popular application. And I forgot to say, so these performance, they spend most of the time in server. They do have the client side. There is a network time, but most of them they spend the time in server. Okay, so next. So I promised that I will tell you some funny mistakes made by programmers. So here they are. So we do a taxonomy. We look at those problems in the latest version, and we also looked at more than 100 problems that are already reported and already resolved in previous versions of these applications. And then we came up with this taxonomy that include 9 we call anti-patterns. 3 big category and 9 small category. The three big categories, the first one is we call them ORM API misuse. The second one, database design. So the idea is that the third one is application design trade-off. So it's like there is a design trade-off that you can make so that your performance can be much better. The first two type is like you don't even need to change your application semantics or display. There's something you can do for your, if you design a database better, if you just with no other change. If you just use a better API, if you use an API in a better way, your performance will be better. Okay, so I will give you some example for each of these. So the API misuse is the biggest problem. It's kind of like the traditional compiler optimization problem. And particularly, I will give you some example for one category we call it inefficient computation, which means you're not generating useless result, right? But you're generating the useful result in an inefficient way. And this unnecessary computation means you're generating result that is not needed. Okay, so the first example. Again, this is in Ruby on Rails, but there's similar problem in all other popular web application framework. So here are three ways to do the same thing, which is to check whether a project, right? So this is from a kind of like a forum, a kind of like a GitHub-ish forum. So this is to, all these three expressions will tell you whether this project contains any issues or not. Okay, so you can tell this one check whether the count is larger than 0, and then here's a .any.exist. Okay, so this here is just random poll. Does any of you know one of these is much faster than the other two? Any guess? Someone say count. Any other guess? Exist? Okay, so it's kind of like a random thing, right? Actually, I don't expect that you would know the answer unless you're a Ruby expert. So turns out, right, the first one actually it's kind of straightforward, this translation. So this will be turned into a select count star query, right? So you count, you really go to the database, you count how many records, right, satisfy the constraint that the project ID field, right, match this project. You get this count and you compare with 0. And the second one, it's the same thing, okay? So it will be translated to do exactly the same thing. And you count, although it does not return the count, right? But it internally does the same thing and compare with 0. Now, the last one, this .exist.any, right? Magically, the last one is translated to a different query. What this query does, okay, it has a limit 1 at the end. So what it does is it searches the table and it stops its search at the first record that satisfies this property, and then it returns. So you can imagine, right, if you have a lot of data, and if you have a lot of data that satisfies this predicate, this is much, much faster than the other two, right? But then there's nothing in the, like if you really search, you can see a lot of people asking this question on a lot of forum. Hey, why their two API have similar name? Actually, why does this API even exist? We don't know, okay? And so this is a real problem. It's in a, actually I was wrong, it's not in a forum. So Spree is a very popular online shopping application. And the developer applied this patch and then immediately 2 times speed up. Okay, and then, so this is one example of this we call inefficient computation, right? You functionality-wise, you get the same result, but your computation is inefficient.
I have a quick question. If I
Yes.
Can you go back to the previous?
Sure.
Does any give you back one of them rather than just a Boolean? Is the difference between exist and any that exist gives a Boolean and any actually gives you one of them?
Yes, so that's a very good question. What I believe, but I could be wrong, what I believe is it also only return a Boolean.
I see. So it really could be implemented. So even if it were kept in the API, the implementation could be changed to be the one for exists.
Yes.
Is that something you suggested to the
We
developers of the
didn't.
API?
I think that there are cases. There are more than one cases that there's this API thing. Like why there was some kind of version saying so. So sometime in the forum, people are saying, for example, for certain API like .any, you should just not use it. But for the historical reason, it's still there. There are also other examples that I will mention later. It's something like yes, it will return a little bit extra data, but you really need a very deep knowledge about the program to make choice.
Okay.
Yeah, that's a good question.
Just a quick question.
Right.
It's like, do you see? But if there is such issue, do you see people changing them in the GitHub or in the open source? Like going from one to the other. Do you see changes of one to the other?
Yes. So you're saying, do people change from any to exist?
Yeah.
Oh, yes, this is. So this is an example that is already fixed.
Yeah.
So it's like originally Spree, they're using .any, and then they changed to .exist. Okay. So the next one. So this one to some extent is not really about API. This piece of code, what it does is they go through, there's an array of values. So this for loop goes through every element in this values array. And then it will check whether this value string is included this u.issues. Okay? So if you just look at this, there's nothing wrong. Okay? Now, the problem is, right, there is an inefficiency here. The problem is this u.issues, this will be translated to a SQL query, right? Who would have thought that? So turns out this u.issue is actually a select query. So issues are not really stored as fields of this u object. So there's a foreign key here. So based on the user ID, then a SQL select query will be sent to this issue, another table, to fetch all these issues. So the patch, so this again is in a fixed problem. So in the patch is simple, right? So you just do this is a loop invariant. So you just do a loop invariant motion here. So you fetch this u.issue, which is a SQL query, okay? You store the result, and then you just do this. Okay, so this is in another very popular, this is a forum web page. You get 20 times speed up. And this, again, is very subtle, right? For people who are not familiar with all this SQL translation thing, you would not expect that this u.issue, which looks like object heap access, is actually a SQL query.
So why doesn't an IDE just highlight the operations that are translated to SQL?
Yeah, good question. So that's exactly what later on we do.
Okay.
So, yeah, so we build an IDE plugin exactly to highlight this. Yes. Yes. So there are a bunch of other examples, and all like if you look at the API, right? There's no one can guess. Like there's something called plug, and there's a map. So the functionality is the same. So what this will do is like plug some ID. It will go to the table. It will find the record. It will go to a particular column, right? Find those records that match this ID and bring those matched records back. If you call map, it will bring the whole column from database to the application server. And then in the application server, it will do the filtering. So actually, this is an example that actually both API has a meaning, right? So it depends. So if later on you will continue to use some other record from, you will continue to use that column, then map will make your follow-up computation better. But if you for this column, if you only need those records that with this ID, you should use this one. It will be much faster, right? And there's some other example. For example, plug size.sum. So this is you will fetch that column size, and then you do a sum in application server. Instead, this one, it will send a SQL query to the database, do the sum there, and then you only bring back the sum. So there's a huge performance difference, but functionality-wise, they're all the same. Okay, so how to tackle this problem, right? So why the existing compiler cannot do the optimization? It's just because the existing compiler, they're not aware, right? They treated all these API as black box. So what we can do, so let me speed up a little bit. So what we did is we just extend the existing compiler so that it will have a knowledge about all these database related things. So the original Ruby code, right? It will be turned into intermediate representation, and you will get a program dependency graph. Now with our extension, the compiler will know that, for example, this will be translated to a SQL query. And then in the program dependency graph, we will put a lot of tags to annotate which are actually queries. And this query is a read or write, which table, which column it will access, and all that. So now with this extended program dependency graph, we can apply all the traditional compiler optimization and solve all these problems. Okay, so, and then exactly, we build this into IDE. So a popular Ruby IDE is called the Ruby Mine. So we added our plugin here, and then it will give you a information, some annotation. It will tell you have an inefficiency here. If you hover here, it will tell you why. And we'll also generate a patch for you, and you can apply a patch and so on. Okay, so so that's the first thing about this API, how to solve this, what are the API problems, how we can solve them. The second problem, big category of problem, database design problem. So this is about sometimes, right, remember a certain type of class automatically map to database table. So when you are doing your class design, you're actually doing database table design. And there will be problems like there's a category called missing field. Like there's certain field, it can be derived from other field. Okay, now the question is, do you always derive them at runtime, or do you save them? Right, so there's a trade-off. So one example, again, this is a fixed problem. It's like in one, I think that's a map application. You can put diary entries onto the map. And in the database, they store longitude and latitude. And then when you try to retrieve your diary entry, it will call API to compute what's the location of this place based on longitude and latitude. So it's very expensive. So the patch is just very simple. You just add an extra field, right, which map to a column in your table, that store the location information. And again, 2 times speed up. And another category that actually happens a lot, but this to some extent is an old problem in database design. A lot of times they missed index, and then that causes problems. So I will not tell you the solution. So actually, Alvin is in the audience. So if I know his group does a lot of work about this part. So. You can ask Alvin about this. Okay, so the last big category is application design trade-off. So this goes beyond the traditional compiler optimization. An example is display design. So, for example, I was telling you this blog, right? And there's a lot of things like, a lot of web page like this, right? You have a long list of things to display. And with time goes, you have more and more things that you want to display. And you have a scroll bar here and allow users to check all these, and these web page take longer and longer time to load. And this happens a lot, and a solution is, right, there's actually a term called pagination. So you could change your display design just so that I only display a fixed number of items. And then there's a navigation bar that the user can go back and forth, right? You can imagine it's a huge performance improvement, but is this worthwhile to do? It depends, right? Okay, so another category, so that was display, right? And so sometimes you want to you have to think about the functionality. It's almost like, to some extent, sometimes approximate result, right, is better considering the performance trade-off. So again, this example, for this web page, sometimes still slow. The reason is, if you look at that, there's a very tiny thing there telling you how many unread blog you have. And for example, in your email, right, you have these like 367 unread email. Do I really care? I don't, right? Sometimes I only need to know I have many unread things. And then by changing from that to this, actually is a great performance speed up. And I have more examples, like for example, here, this is a story, this is a forum, and some people say, hey, it takes a long time to just load this page. And there's nothing on this page, right? There's no content on this page. Why? It takes almost 2 seconds to load. Why? It turns out the application, the developer wants to show this guideline conditionally. So they will do a join query to find out the one who planned to submit this story, whether you're an experienced user or not. If you're not an experienced user, then I will show you this guideline. And this query, it takes about 1 second to run. Right? And then so after the user they're saying this is just ridiculous, right? And then what they decide to do is they just shrink all this to a link, right? So they delete this query. So they always have a guideline link. If you want to click it, right? So again, so this is about there's functionality trade-off. So the solution, right? And we realized that, so this is in this year's ICSI work. So we realized that this is not something compiler wants to automatically do, right, without letting developer know, because developer should be involved in making these decisions. So what we can do is we can give information, right, to the users about what's the cost of different tags on your web page. And then we can automatically synthesize alternative design, right, display design and functionality design to help the developer to quickly make the right decision. So quickly go through this example. Now, if you use our tool, in addition to just seeing this web page, you will see a heat map, right? So this heat map is, again, remember that we have extended program compiler analysis now, right? So that not only have database information, also it will connect, it will also analyze this HTML so that it will know every your HTML entry, right? We'll do a slicing so that we know what computation, what query went into getting the data. So then we'll do a query complexity analysis, and then we can show you the complexity cost heat map. And then we have some JavaScript engine so that if you clip it, we will do the program analysis and we'll tell you, hey, this piece of code, right, if you want to simplify, you can potentially use pagination. And if you click pagination, then we will make change in the IDE. We will show you here the changes, and then automatically we will rerun the cost analysis. And then pagination is actually relatively easy. We also do, for example, for this one, we will tell you, hey, here you can try asynchronous loading. You can try approximation, you can try remove. There are more program analysis went behind this. So for example, for asynchronous loading, right? So which means that 1001, that data, it will be loaded not separately from the other part of this web page. So we will do data dependency analysis to see if there's some common query, right, that is used by both this part and that part. Then it doesn't make sense to make one of them asynchronously loaded. So there will be more program dependency analysis behind some of this. And similarly, we will automate all the program change, and so that the developer will have an easy way to to make a decision. Okay, so again, we tried this on this 12, the latest version of this 12 popular application, and we find more than 100 performance enhancing opportunities there. We also did a user study, right? Because some of this, it depends, right? Some people may like a pagination, some may not like. We did a thorough user study, and we found that indeed, by doing this change, you get more benefit. You get a better rating regarding how users will like this. And actually, to some extent, it's funny. Sometimes we have things that we simply remove an entry, and we ask a user which web page you like better. And then people say, I like the ones with some of the content removed. So it's a tough job to being a web page designer. Okay, so in summary, for all these things about this replication side. So I hope that you see that it's difficult to write not just correct, right, but also well-performing applications that have a database backend. And this interface, because of this interface of database, right, and then traditional object-oriented programming, because of this interface, there's some performance gap there. And yeah, so you can try our plugin, try our tool, and feel free to let us know if any comment. Okay, so I will use 5 minutes to quickly go through the other side that I promised. So what stopped cloud service? So a lot of this is done in collaboration with Microsoft. So there were a lot of study, right? So there were a lot of study about what stopped desktop application, right? And there were also some study about what are the bugs in open source distributed software, right? So including my own group, we did those study. But though all those previous studies, right, these are all about bugs that you find during in-house testing, right, in the Bugzilla. It's unclear what are the problems that actually happen in the field that actually cause end users to suffer. So because of that, so we take 6 months high severity incidents from Microsoft Azure service. So this is after deployment, and these are the real problems that Azure customers encounter. And then we try to see what caused the problem, how they were handled. Okay, so a little bit background, like what caused problem in non-cloud software. There are many different studies, but roughly speaking, it's like 1/3 software problem, 1/3 hardware problem, 1/3 human operation error. Now, in this Azure study, some highlights. First of all, there are only about 2% of problems that they contribute to hardware problem. Okay, and probably a large reason is the software are expected to cover some hardware errors because of distributed systems are supposed to have redundancy. So we think that's why this percentage dropped significantly. And then general semantic error, the percentage also dropped significantly. What was here? Sorry, the memory bugs. Actually, we didn't see any traditional memory bug like buffer overflow, something like a memory leak. We only see a small number of resource leaks, which are actually virtual machine leak, are not traditional memory bug. We didn't see any uninitialized read, dangling pointer, none of that. And there is a jump on concurrency bugs, including races on objects and races on persistent data. Okay, there are a few other types of interesting bugs that are very popular. And the other takeaway point is we find that more than 50% of problems, they were solved during the runtime, right? There was no patch released. And the developer just came up with some mitigation method, like let's kill a process, let's delete some data, and let's see whether it works. Oh, it works, okay, then let's just tell the customer everything's good now. How to solve this problem? So we tried a lot of things in the past, tried to detect timing bugs, and we were able to find a very small number, 5, 6 bugs, and finally, so in this year's SSP paper, we completely give up on happen before analysis. If some of you know, it's a very heavyweight program analysis, and we use more a combination of like random fault injection and take some feedback, make adjustment at runtime, and we were able to find like more than 1,000 bugs with very little overhead. And we're also trying to do something about fixing. Okay, I don't have time to go through. It's just that so actually the tool that we built that find more than 1,000 Azure code with Microsoft people, the code is actually open source now. So feel free to try it and maybe improve it. Okay, so that's all. And I guess the takeaway message is there's still a lot of bugs. And we have more and more new type of software, and the bugs are just take on new forms. Okay, and I want to thank my collaborators. Thanks very much. Okay.
Okay, we can take some questions.
This is Mohammed from University of Bern. Thank you, Shan, for the talk. It was quite interesting. In terms of API misuses, I'm wondering to which extent do you think it's possible that we apply the optimization on the database engine? Because I think the computation and the current analysis is very heavily dependent on the underlying ORM at the moment.
Yeah, that's a good question. The question about if we just apply optimization on the database engine, database side. Yep. Is that, yeah, so actually there are already a lot of work on the traditional database optimization, right? So the problem is without a high-level application semantics, right? There's only that much the database can know. So for example, right? So suppose I send one, like in that loop environment, so in that loop example, right? So like I keep sending the same SQL request, right? I always get the same result. So because the database engine does not know what are the next 100 requests, there's only that much database engine can do, right? So database engine can say, oh, I've observed 10 requests, it's the same. Then maybe let me cache the result, right? So that is better. But still, you still have to pay the cost of sending the result to the application, right? So the purpose, the big idea, right? The takeaway message behind our work is exactly, you don't want to do just optimization only in database, right? Or only in the application. You want to bring these two together, and then you can do much better. Right, but yeah, there are more. We believe there are you can do better database optimization.
So have you tried to see what is the trade-off between the two? Because I think one of the examples that you've shown, for example, the one which is counting the number of rows in the database, that could have been done in the database on the database side and then be just fetched from the database, rather than being an optimization on the application side and then sending the request to the database.
So I guess your question is like whether it's better to do it in database or whether it's better to do it in
actually, based on what you said, I think there should be a trade-off between for which API users you might decide to delegate the optimization to the database, and for which one you need to do this on the application.
Yes. So actually, I think Alvin has some work about just to decide whether to delegate or not, right? Because sometimes there's a trade-off between, say, the network, right? It depends on how much data is generated, right? So what's the network cost? What is computation cost? What is it? So I think there are optimization you can do by considering all these. I think that is a direction. And then there's just also other cases, like some of the example I mentioned. It's kind of like to some extent, there's no trade-off. It's like you just don't need to do that computation at all, right? But in other cases, yes, there is a trade-off. Potentially, if you have a cost model or something, then you can do better. You can do better optimization decision.
All right. Any other questions?
I have a follow-up question about some of the new work that you did on the Azure study. So is it a test generation and also workload generation you say you found thousands of bugs, right? So one, I want to know whether it is input generation or workload generation. The other thing is in these cloud systems, how do you define bug, right?
Yes.
Are you looking at some sort of failures or exceptions or crashes or what? you
Yeah.
mentioned also semantic bug.
Yeah, that's a
which
very good
oftentimes
question.
we don't have a test oracle.
Yes,
right?
exactly. Yeah, so actually, to be honest, like kind of we take advantage of the test cases and the test oracles that are already developed in Azure. So it's just that those test cases, so basically in Azure they were already, so they have something called a cloud-built environment. They already written a lot of unit tests, test input oracle are all there. So that's not what our work is about. Our work is just about, because those are all multi-threaded or asynchronous program. So in the past, they do not test the timing part. You just run this test case once. You see whether the test oracle is correct or not, right? And now what we do is, when you run it, we will inject delay at selective places, and then we see whether your test pass or not. So yeah, so we did not do anything to help the test case generation oracle, and the way that we can judge this a bug or not is leveraging existing test oracle. So what we do is just generate a delay.
Okay. So just a very quick question, right? So it's very impressive you find like a couple thousand bugs. How many more are there?
Yeah, that's a very good question. So, so for the later part, like the one that we find more than 1,000 in Microsoft code. So later on, because in that particular piece of work, we emphasize about overhead. So we want to run the program once and find a bug. So then later on, we actually did some testing. We have a benchmark with 3,000 module, and then we just run for as many times as we can. And it's something like, for that small set, we found like 50, we found about 60 in 2 runs. And when we run it 100 times, we see it kind of saturated at about 90. So it's like, I would imagine there are at least so it's like from 60 to 90, I would assume there are probably another 500 bugs there. Yes.
All right. So let's thank Shan for the very interesting talk.